Welcome, ladies and gentlemen, to this video lecture. Okay, so now we will set out to prove theorem 4.3.2, the fundamental theorem of calculus. So let's just read this theorem again. So we have a continuous function, little f. We define big F as this integral with little f as integrand. And then the conclusion of the statement is that big F is continuous, and on the big F is continuous on the closed interval, big F is differentiable on the open interval, and we know what the derivative of big F is. The derivative of big F is little f at any x in our open interval. Okay, so let us think about how we will go about proving this theorem. So the first thing is we assume that little f is continuous. That forms part of the statement, and this we will have to use in writing our proof. And remember what this means. This means that the function value of little f anywhere on this interval is equal to the limit of f of x as x tends to any point in that function value. So remember the definition of continuity. So we will look at this statement first. So that f is differentiable, and show that its derivative is equal to little f. So what do we need to show? We need to show for any point C that capital F is differentiable at little c, and the derivative at c of big F is equal to little f at c. So that is what we need to prove. So, but this word differentiable means something very specific. So let's write out exactly what this means. So that f is differentiable and its derivative is equal to little f. This means that the limit as h goes to 0 of f of c plus h minus f of c over h is equal to little f of c. So this is what it means. And if we look at theorem 3.3.7, this statement is equivalent to, so by theorem 3.3.7, this statement is equivalent to the following. So that the limit as h tends to 0 from the right of f of c plus h minus f of c over h is equal to little f of c, and the limit of h tends to 0 from the left of f of c plus h minus f of c over h is equal to little f of c. So this statement that we claim to be true is equivalent to both of these statements being true. So if we can prove both of these statements, then we are done, and we are done by theorem 3.3.7. So I'm going to label this R, and I'm going to label this statement L. So if we prove both R and L, then we are done showing that F, capital F, is differentiable. So what we will do is we will prove R, and we will leave L as an exercise. Okay, so before we do anything, let us write a proof outline for R. So proof outline. For R. Okay, so firstly, what are we assuming? We assume that f is continuous on our interval AB. Then we want to show that this limit exists and is equal to little f of c. So now remember, this statement means something very, very specific. So what does it mean? It means for every epsilon there exists a delta, so that if h is between 0 and this delta, then this expression is within an epsilon distance of f of c. So let's write down our outline there. So we want to show for any epsilon greater than 0, so fix any epsilon greater than 0, fix any epsilon greater than 0. Then we want to define delta as something we don't yet know, but it must be positive. And what are we allowed to use? We are allowed to use epsilon there. We're allowed to use any of our previously defined symbols. And then we want to show if, now since we are taking our limit as h tends to 0 to the right, we want to show that if h is between 0 and delta, then something happens. So we will assume h is between 0 and delta, and now we want to prove that this expression that we have here is within an epsilon distance of little f of c. So now we want to consider f of c plus h minus f of c over h minus little f of c, and here we now want to do some work and finally conclude that this expression is less than epsilon. So here is the outline for our proof, and we have to keep in mind that we will have to use that little f is continuous on AB. So remember, when we make an assumption like this, we can treat it like a shop. So remember the definition of continuity. It says that a certain limit exists, but if we remember the definition of the limit, for every epsilon there exists a delta. So if we bring an epsilon or any positive number to the shop will sell us a delta, which will do something. So just keep that in mind as we go along. Okay, so here we have now written a proof outline. So we have not filled in all the details, but our proof will have all of these elements in it when we complete it. Okay, so I will see you in the next one, where we will complete this proof.